Of electrochemistry, we study about conductors. Conductors are the substances that allow the flow of electricity. Now they can be classified into two types. One is electronic conductors and one is electrolytic conductors. In electronic conductors, conduction happens due to migration of electrons. They do not involve transfer of matter. They do not involve any chemical changes. The resistance increases with the conductivity. Sorry, there's a mistake. The resistance increases while the conductivity decreases, where during the reaction the temperature will increase. An example of this could be metallic conductors. Electrolytic conductors. This conduction happens due to migration of positive and negative ions towards the respective electrodes. Involves transfer of matter. The current flow is accompanied by electrical changes. Due to the changes, we have current. Resistance decreases, conductivity increases while there's increase in temperature during the reactions. An example for this could be molten electrolyte or its aqueous solution. We also have electrochemical cells. They can be classified as electrolytic or voltaic or galvanic cells. In electrolytic cells, conversion of electrical energy happens due to chemical energy. In this, positive electrode is anode where the oxidation occurs, and the negative electrode is the cathode. Non-spontaneous reaction is forced to occur by electric current. The direct current from an external source is used. The electrodes are used and the process is called electrolysis. And therefore these cells are called electrolytic cells. An example for this could be purification of metals. Under voltaic or galvanic cells, the conversion of chemical energy is with electrical energy. In this, negative electrode is anode where the oxidation occurs, and the positive electrode is cathode where the reduction occurs. You see, they are opposites of each other. Spontaneous chemical reaction occurs by itself and generates electricity. The direct current is produced by cell due to spontaneous chemical reactions. As compared to electrolytic cells, an external battery or power is not required. Examples for this could be a dry cell, a fuel cell, or a lead storage cell. These are the electrochemical cells. We are now going to see different types of cells and batteries. The first one is a dry cell. It has an EMF of 1.5 volts. The anode used here is zinc. The cathode used is carbon in the form of a graphite rod. The electrolyte used here is NH4Cl plus ZnCl2. This is around the anode. The cell reaction for the anode is given by where it turns zinc in solid state turns into an aqueous state, and the cathode is giving us plus Mn2O3 in the solid state plus 2NH3 in the aqueous state plus H2O in the liquid state. These are your cell reactions. And the overall reaction would be given as zinc in the solid state plus 2NH4 plus in the aqueous state plus 2MnO2 in the solid state, giving us Zn2 plus in the aqueous state plus Mn2O3 in the solid state plus 2NH3 in the aqueous state plus water, which would be in the liquid state. The next is the lead storage battery. The EMF produced is 2 volts. The anode used here is a lead grid packed with spongy lead. This will be a lead grid packed with spongy lead. The cathode used here is a lead grid packed with lead O2, PbO2. The electrolyte used here is a 38% H2SO4 solution. The cell reaction at the anode would be lead in the solid state plus SO4 2 minus in an aqueous state, giving us PbSO4 in the solid state plus 2 electrons, and at the cathode we would have PbO2 in the solid state plus 4H plus in the aqueous state plus SO4 2 minus in the aqueous state, giving us, in addition they have 2 electrons, giving us PbSO4 the solid state plus 2H2O in the liquid state. The overall reaction can be written as lead in the solid state plus PbO2 in the solid state plus 2H2SO4 in the aqueous state, giving us 2PbSO4 in the solid state plus 2H2O in the liquid state. Next we have nickel cadmium cell, which is also called NECAD cell. The EMF produced is 1.4 volts. For the anode we use cadmium. For the cathode we use NiO2 supported over nickel. The electrolyte used here is KOH solution. The cell reaction that happens at the anode can be given by CD in the solid state plus 2OH minus in the aqueous state, giving us CdOH twice in the solid state plus 2 electrons. At the cathode we have NiO2 in the solid state plus 2H2O in the liquid state plus 2 electrons, giving us NiOH twice in the solid state plus 2OH minus in the aqueous state. The overall reaction can be written by cadmium in the solid state plus NiO2 in the solid state plus 2H2O in the liquid state, giving us CdOH twice in the solid state plus NiOH twice in the solid state. The next is hydrogen oxygen fuel cell. The EMF produced by it is 1.23 volts. The anode used is porous carbon with PT. And the cathode used here is same porous carbon C with PT. The electrolyte used here is the aqueous solution, which is concentrated. KOH. The cell reaction that happens in this cell can be represented by 2H2 in the gaseous state plus 4OH minus in the aqueous state, giving us 4H2O in the liquid state plus 4 electrons. The cathode, this was the anode. The cathode reaction can be given as O2 in the gaseous state plus 2H2O in the liquid state plus 4 electrons, giving us 4OH minus in the aqueous state. The overall reaction for this cell can be written as 2H2 in the gaseous state plus O2 in the gaseous state, giving us 2H2O in the liquid state. We are going to look at some important formulae in the chapter of electrochemistry. The first one is cell constant. represented by B, which is L by A, where L is the distance between the electrodes and A is the area of cross section of the electrode. The second one is the electric conductance G. It can be given by G is equal to L by R. 1 by R, sorry, which is R stands for the resistance. The third is molar conductivity. This can be represented by kV or 1000 K by C, where V stands for volume of the solution in centimeter cube, C is the concentration, and alpha is represented by this, where alpha is the degree of dissociation, this is the molar conductivity, and this is the limiting molar conductivity. K is equal to where K is the dissociation constant. Next is Faraday's laws. In the first law, we see the quantity of electricity passed. It can be given as Q is equal to IT, where Q is the quantity of electricity, I is the quantity of electric current, and T stands for time. Second, number of electrons passed in moles. It can be given by Q of C by 96500, which is in terms of C per mole electron, where 96500 is the charge of 1 mole electron as given here. Thirdly, the number of moles of product formed. It can be given by the number of moles of electrons passed into the mole ratio. Therefore, we can write mole ratio is equal to moles of product formed in half reaction upon the moles of electrons required in the half reaction. Next, we calculate the mass of the product formed. It can be given by two parts. First, moles of the substance produced, which is equal to I of A into T of S 96500 in the terms of C per mole electron into the mole ratio. And secondly, mass of the substance produced, which can be given as I in the terms of amperes into T in the terms of second upon 96,500 in the terms of C per mole electron into mole ratio the whole into molar mass of the substance. Next, we see Faraday's second law, which states moles of A produced upon moles of B produced equals mole ratio of A half reaction upon mole ratio of B half reaction. Next, we see the EMF of a cell. It can be written as the E of a cathode minus E of the anode, where this is a standard cell potential, this is the standard potential of the cathode, and this stands for the standard potential of an anode. Next, we'll see the Nernst equation. E of cell is equal to E degrees of cell minus 0.592 by N log of products upon reactants. Or another form for Nernst equation is E of cell equals E degrees of cell minus 0.059 by N log of 1 by m raised to n plus. Next is the cell potential and Gibbs energy changes for cell reaction. It can be given as cell potential and Gibbs energy. It can be given as delta R of G degrees is equal to minus NFE of cell, where delta R G degrees is a standard Gibbs energy change, N stands for number of electrons gained or lost, and E degrees of cell is the standard electrode potential. Next, we calculate the standard cell potential and equilibrium constant. It can be calculated by the following formula. E degrees of cell is equal to 0.059 by N log K, where E cell is 0 at equilibrium and K is the equilibrium constant.
Question 1. The weight of a silver, that is atomic weight, is given as 108, that is 108, displaced by quantity of electricity which displaces 5600 ml of O2 at standard temperature and pressure, that is STP, will be, we're given four options. At STP, that is standard temperature and pressure, 22,400 of ml of O2 is equivalent to 32 gram of O2, that is 1 mole of O2 oxygen. 5600 ml of O2 will be equivalent to 8 gram of O2 at STP. So weight of O2 displaced in grams will be given as WO2 equal to 8 grams. So equivalent weight of a silver, that is EAG, 108 upon 1 equal to 108. And equivalent weight of O2, that is E of O2, is equal to half into 32 upon 2, which we get equal to as 8. So by using Faraday's second law of electrolysis, we have mass of silver, that is WAG, upon mass of oxygen, that is WO2, equal to equivalent weight of silver upon equivalent weight of oxygen. Substituting this value, we can find the value of mass of silver, that is weight of silver, we get as WAG equal to 108 upon 8 into 8. Solving this, we get 108 grams, which is our answer matches with option D. Therefore, option D is the correct answer. Question 2. 1 gram of which of the following compound will require maximum amount of electricity for the decomposition? We have four options as AgNO3, B AlCl3, C CuCl2, and D MgSO4. For the first option, we know that Ag plus of E electron, when we add electron we get Ag. So in AgNO3, to deposit 1 mole of Ag, one Faraday of electricity is required, that is Al plus 3 plus of 3 minus gives us Al. In AlCl3, to deposit 1 mole of Al, that is aluminium, it needs 3 Faraday of electricity is required. Now for the copper, we have copper C plus of 2 E. When we add this, we get copper. So in CuCl2, to deposit 1 mole of copper, 2 Faraday electricity is required. Same way for Mg, that is Mg plus of 2 plus of 2E, we get Mg. So for MgSO4, that is magnesium sulfate, to deposit 1 mole of Mg, 2 Faraday of electricity is required. So comparing with all 4 options, we see that AlCl3 solution will require maximum electricity compared to all 3 options. Therefore AlCl3 is a correct answer, which is option B. Therefore option B is a correct answer. Question 3. Number of electron required to reduce 4.5 into 10 raised to minus 5 gram of aluminum is. We are given 4 options. Aluminium, that is Al plus of 3, needs 3 electrons to give aluminium. So the 3 Faraday charge is required to deposit 27 gram of aluminium. That is 3 Faraday is required to deposit 27 gram of aluminium. So the X Faraday of charge required to deposit 4.5 into 10 raised to minus 5 gram of aluminium can be found as X equal to 3 into 4.5 into 10 raised to minus 5 upon 27. That is Faraday. Now 1 Faraday is equal to charge on 6.022 into 10 raised to 23 electrons. Number of electrons required is equal to 3 into 4.5 into 10 raised to minus 5 upon 27 into 6.022 into 10 raised to 23. Solving this, we get 3.0 into 10 raised to 18 electrons, which is equal to, our answer matches with C. Therefore option C is a correct answer. Question 4. The EMF of galvanic cell with oxidation potential of zinc, which is equal to plus of 0.76 volt, and that of copper minus 0.34 volt is. We're given 4 options. The reduction potential of an electrode is always equal to its oxidation potential with the sign reverse. Therefore the reduction potential of zinc, which is equal to minus 0.76 volt, and that of copper should be plus of 0.34 volt. So the electrode with a higher reduction potential forms cathode. So copper is cathode and zinc is anode. Therefore E cell equal to E cathode minus of E anode. We substitute both the values, we get 0.34 minus of minus 0.76. Adding both this, we get 1.10 volt, which is in positive when we. So therefore we get 1.10, which our answer matches with option B, that is plus of 1.1. Therefore option B is a correct answer. Question 5. At temperature of 298 Kelvin, the EMF of the following electrochemical cell as given will be, where standard cell potential is given as equal to minus 1.562 volt. For the given electrochemical cell, the oxidation reaction at anode, the reduction reaction at cathode, and overall cell reaction are as follows, can be written as 2Ag plus of 2E. If we see this is an oxidation at anode. Zinc of +2 E zinc. If we see this is a reduction at cathode. So the overall reaction can be written as 2 Ag plus of zinc gives us 2 Ag plus of zinc. So the EMF cell is given as E cell equal to standard cell potential, that is E cell minus of 0.0592 upon n log to the base 10 Ag plus of 2 square upon zinc plus of 2. Substituting the value in the above equation, we get E cell equal to minus 1.562 minus 0.592 upon 2 log to the base 10 0.1 the whole square upon 0.1, which is equal to minus 1.62 minus 0.0592 upon 2, which we get this as log to the base 10 raised to minus 1. Solving further, we get minus 1.562 minus 1.592 upon 2. Further we solve this, we get minus 1.562 plus of 0.0296. Subtracting, we get as minus of 1.5324 volt, which is we get as E cell equal to minus 1.4324, which is our option A. Therefore our answer matches with option A. Therefore option A is a correct answer.